everyone. Today we're going to be covering the respiratory system. These are the CLOs, and then these are the objectives. So explain the process of inhale, explain the process of exhale. Describe all of the lung volumes and lung capacities. Explain the following terms and the disturbance. Metabolic acidosis, metabolic alkalosis, respiratory acidosis, as well as respiratory alkalosis. Okay. Now, the lungs actually has two types of cells. It has type 1 pneumocytes and type 2 pneumocytes. Type 1 and type 2 have two different functions. Type 1 pneumocyte is the epithelium. It's a squamous epithelium that actually does the gas exchange. Whereas type 2 pneumocyte actually produces a substance called surfactant. Now, what is the importance of surfactants? The function of surfactant is to decrease the surface tension. Therefore, during exhale, our lungs do not collapse. Now, what is surfactants? What is it made up of? So it's basically a fluid which is composed of lipid and protein. Okay? Now, what surfactant does, as I said, it decreases the surface tension. But it actually goes and lines the alveoli, the inner surface of the alveoli. And therefore, when we exhale, that surface tension, which is the surfactant which is lining the alveoli, decreases surface tension during exhale. When does surfactant start getting produced? After 24 weeks of gestation, this is when type 2 pneumocytes within the lungs start producing surfactant. But surfactant does not line the alveoli until during delivery. So when the baby is being delivered and going through the birth canal, it's very stressful for the baby. That causes a hormone called cortisol to be released. And cortisol actually causes the type 2 pneumocytes to secrete surfactant, which will go and line the alveoli, thereby allowing surface tension to be decreased when the baby takes its first breath. As you know, during utero, the baby does not breathe, and this is why at that time, surfactant was not needed in the lungs. Now, let's talk about respiration. What is respiration? Is a movement of gases between the atmosphere and the body cells. There are two types of respiration. There's internal respiration, and then there's external respiration. External respiration is also called ventilation, and this is the respiration that is occurring between the atmosphere and the lungs, basically the gas exchange. Internal respiration is a gas exchange occurring within our cells, between the cell and the capillary and the alveoli, where external respiration was getting the air into the lungs and having the air move out of the lungs. That was external. One key thing, air always flows due to pressure or gradient difference. It always goes from high to low. As mentioned, internal respiration is a gas exchange that occurs between alveoli and red blood cells and tissues. External respiration or ventilation is air movement between lungs and the atmosphere. Inhale is a part of external respiration where air moves into the lungs. Well, exhale is part of respiration, external respiration, where air is moved out of the lungs. Okay. Let's quickly touch base on the air. Air is all around us, and it actually goes all the way up to stratosphere. Okay? Now, barometer is a technique to check how much pressure does air exert on us. Okay? At sea level, the atmospheric pressure is 760 millimeters per mercury, meaning that's how much pressure air is actually pushing on us at sea level. Boyle's law states that pressure and volume are inversely proportional. As you increase the pressure, the volume decreases, or as you increase the volume, the pressure decreases. Certain terms, intrapulmonary pressure means pressure inside the lungs. Intrapulmonary volume means volume or inside the lungs. Okay. Rest. When you're resting, this is right between inhale and exhale, temporarily for a short time frame, your body's at rest. It's neither inhaling, neither exhaling. The atmospheric pressure and the intrapulmonary pressure at that time is the same. So imagine this is atmospheric pressure. This is the intrapulmonary pressure, pressure within the lungs. It is the same, 760 millimeters per mercury, 760 millimeters per mercury. Okay? Air neither enters or leaves the lungs. Why? As I mentioned, everything always goes from high to low. But if both areas are unequal, there is no gradient for air movement. Everything is the same. So no pressure difference occurs at that time because air always moves from high to low. Blood levels at rest. Oxygen levels are low, whereas carbon dioxide levels in the blood are high. So at rest, CO2 is low, carbon dioxide is high. Lung volume at rest is around 400 milliliters of air. Now, we're going to see how our body is able to inhale. How do you do inspiration? So how do we make air enter the lungs if the two areas are equal? So if the atmospheric pressure and the intrapulmonary pressure is equal, how do we make air go into our lungs? Now, we can't change the air in the atmosphere, correct? You cannot change the pressure, but we are able to change the pressure inside our lungs. So if we want air to leave the atmosphere, enter our lungs, we have to decrease the pressure in our lungs, okay? So when you do that, when you decrease the pressure within our lungs, the atmosphere becomes high, the lung pressure becomes low, air can leave the atmosphere, enter the lungs. And essentially that's what happens during inhale. But how? Now the question is, how do we actually change the pressure within the lungs? We do this by actually changing the volume inside the lungs. Remember the Boyle's law? The volume and pressure are inversely proportional. So if we want the intrapulmonary pressure to decrease, we must increase the intrapulmonary volume. So step by step, you're going to learn how inhale works. How are we going to actually cause the intrapulmonary volume to increase, thereby intrapulmonary pressure can decrease. And then once the intrapulmonary pressure has decreased, what happens? This is a step-by-step process of how inhale happens, and you have to know it step by step. Okay, so as I mentioned, for respiration or inspiration, the intrapulmonary pressure must be less than the atmospheric pressure. So we must decrease the intrapulmonary pressure. How do we do that? We do this by increasing intrapulmonary pressure. So this is a flow chart, very easy to follow. At rest, our blood levels are low oxygen, high carbon dioxide. That low oxygen, high carbon dioxide will stimulate the chemoreceptors. What are chemoreceptors? They are receptors that respond to chemicals. Oxygen, carbon dioxide are considered chemicals. Once the chemoreceptors are stimulated, they in turn stimulate the medulla oblongata, which is the respiratory center. Once the respiratory center has been activated, it tends to stimulate the phrenic nerve. Phrenic nerve is a nerve associated with respiration. Phrenic nerve actually innervates the diaphragm and the respiratory muscles. So when you stimulate the phrenic nerve, it actually stimulates the diaphragm and the respiratory muscles. Therefore, the diaphragm moves down, respiratory muscles move move outward. Because the diaphragm has moved down, respiratory muscles have moved outward, it actually pulls the lung in every direction. And now because the lung has been pulled in every direction, it creates a negative pressure within the lungs. Okay? So because the diaphragm and the respiratory muscles are stimulated, it pulls the lungs, causing a negative pressure to be generated within the lungs. Now, this negative pressure actually acts like a vacuum. Imagine that you're at your home, you're studying for physiology, you have your notes everywhere, okay? And then all of a sudden, somebody in your household turns on the vacuum. What happens to all those papers? They get sucked in, correct? That's because the vacuum is the negative pressure and it's sucking stuff in. Essentially, that's the same thing that happens in our lungs. Because there is a negative pressure that we just created within the lungs, it actually causes thoracic veins to drain blood into the lungs. So, negative pressure is created inside the lungs that causes thoracic veins to drain blood into the lungs. Now, because you have just poured blood into the lungs, which is basically now you have increased the volume. So there's increase in intrapulmonary volume. Once you increase the volume, the pressure decreases. So there is a decrease in the intrapulmonary pressure. And now because the pressure has dropped, okay, so now you have just caused the intrapulmonary pressure to drop. Basically, atmospheric pressure is higher. The decrease in intrapulmonary pressure just by 4 millimeters per mercury causes air to enter the lungs. So air will actually leave the atmosphere, enter the lungs, and this is how we inhale. Okay. Now, since we actually touched base on chemoreceptors, let's actually talk about the different chemoreceptors and where do we find them. There are two types of chemoreceptors. One of them is called central chemoreceptor, another one is called peripheral chemoreceptor. Central chemoreceptors are type 1, peripheral chemoreceptors are type 2. I'm going to start with peripheral and then I'll come back to central. Peripheral chemoreceptors actually detect the levels of oxygen. And where are they located? They're found in the carotid artery and the aortic bodies. They actually respond to decreased levels of oxygen. So any time that oxygen levels is decreased in our bloodstream, the peripheral chemoreceptors located in the carotid artery and aortic bodies will get stimulated. Okay? Now, let's talk about the central chemoreceptors. Central chemoreceptors are responsible for detecting carbon dioxide, but they don't directly look at how much carbon dioxide there is in blood. They actually look at hydrogen concentration in the CSF, cerebrospinal fluid. Okay? So central chemoreceptors are found right around the respiratory center, okay, the medulla oblongata, and their function is to monitor the hydrogen levels in the CSF. Anytime there's an increase in hydrogen levels in the CSF, it tells them that there is high levels of carbon dioxide and it gets stimulated. So what happens once these chemoreceptors get stimulated? As my previous slide said, anytime peripheral chemoreceptors get stimulated or central chemoreceptors get stimulated, they tend to stimulate the respiratory center. Okay? It's basically telling our body that we need to take a breath, basically. Now, between the two, central chemoreceptors are the boss. So, if peripheral chemoreceptors are saying that there's normal level of oxygen and they don't get stimulated, where central chemoreceptors detect there's a high level of CO2, well, indirectly because they detect high levels of hydrogen, therefore there are high levels of CO2, it actually stimulates the respiratory center. Okay? So, central chemoreceptors are the boss. It will override peripheral chemoreceptors if they're giving two opposite information to the respiratory center. The central chemoreceptors and the peripheral chemoreceptors in turn can both be overcome or disobeyed if the higher brain centers tell them to do so. Meaning, right now, if you guys, all of you take a deep breath, increase your breathing rate. You can all do that, right? You don't have low oxygen, you don't have a lot of hydrogen, meaning CO2, but why is it that your respiratory rate can increase? You can breathe really fast. Because your higher brain centers are telling you. So higher brain centers, like your cerebral cortex, can override and the central and peripheral chemoreceptors and tell the respiratory center what it wants it to do. Okay? So this is a slide just showing you the central and peripheral chemoreceptors as well as basically the cerebral cortex, the higher brain centers. Okay. So we talked about inhale. Now we're going to talk about exhale and how that happens again step by step. Now remember, at rest, atmospheric pressure, intrapulmonary pressure were equal. During inhale, we actually caused the intrapulmonary pressure to decrease. This is why air went in. But now, during exhale, we actually want air to leave the lungs. How do we do that? We actually have to cause this intrapulmonary pressure to rise and not reach 760, even go beyond. It has to reach 764. Again, a 4 millimeter mercury difference. So now the intrapulmonary pressure is higher than the atmospheric pressure and air can leave. Okay? That's what we're going to do. So now we're going to learn how do we cause our intrapulmonary pressure, which was at 756, how do we cause it to go up and even beyond 760, therefore it reaches 764. So of course, to bring your intrapulmonary pressure up, you have to decrease the intrapulmonary volume because pressure and volume are inversely proportional. So let's see. When you inhaled, when you actually took air in, it actually caused your lungs to basically stretch. So inhalation caused your lungs to be filled with air. That actually caused your lungs to stretch. And because your lungs expanded, it actually stimulated the stress receptors within the medulla. Once these stress receptors were stimulated within the medulla oblongata, that in turn inhibits the phrenic nerve. So now the phrenic nerve is no longer being stimulated. If the phrenic nerve is no longer being stimulated, it is no longer innervating or stimulating the diaphragm and the respiratory muscles. Thereby, the diaphragm and the muscles tends to relax. So the diaphragm moves back up, respiratory muscles move inward, okay? Because now they're relaxed. So when the diaphragm and the respiratory muscles relax, it actually causes the diaphragm to move up, respiratory muscles to move inward. That causes the lung to fall back on itself because the lung is filled with elastic fibers. It's like a rubber band. Once you relax it, it kind of comes back to its original shape and size. Same concept. You pulled the lungs during inhale, you stretched it. Now exhale, you kind of release them and they're going to fall back and become its original shape and size. So when the lung falls back on itself because of this recoiling property, blood is pushed out of the lungs via the arteries. Because blood is pushed out, there's a decrease in intrapulmonary volume. Because you have decreased the amount of volume inside the lungs, automatically there is an increase in intrapulmonary pressure by 8 millimeters per mercury, meaning you were at 756, you went up to 760, but you kept on going and reached 764. So it went from 56 to 64, which is 8 millimeters per mercury difference. And that difference in, intrapulmonary pressure and the atmospheric pressure causes air to leave the lungs, enter the atmosphere. So air leaves lungs, and that's how we exhale. Okay. This is basically a spirometer that basically checks the lung volumes and lung capacities. Let's do question 1. So because it's telling it's looking for central chemoreceptors, okay? Central chemoreceptors are found by the medulla oblongata. So the probe will actually go by the medulla oblongata. Question 2. So it tells you that he stimulates the central chemoreceptors. Do you guys remember what the central chemoreceptor responded to? They responded to the CO2 levels by actually looking at hydrogen levels. So if he wants to stimulate them, he has to add hydrogen, because now if the hydrogen levels are increasing inside the CSF, it will stimulate the central chemoreceptors. Okay, now let's look at the lung volume and the lung capacities. So in this slide, I'm just identifying the names. In the next one, I'll explain what each one means. So we're going to start with this, TV, tidal volume. Okay, tidal volume is this wave right here. Then let's look at IRV, inspiratory reserve volume. It's this right here. It's from here to here. That's inspiratory reserve volume. Let's look at ERV, expiratory reserve volume, which is this part right here. Okay? Then look at RV, residual volume, which is this part right here. Let's look at EC, which is expiratory capacity. It is this area right here. Let's look at IC, inspiratory capacity. It's this right here. Let's look at VC, vital capacity, which is all of this right here. Let's look at FRC, which is functional residual capacity, which is this area right here. Okay? And then look at TLC, total lung capacity, which is all of this. Okay. Now let's see what each thing means. So tidal volume is one normal breath. So a normal inhale and a normal exhale. That's tidal volume. Now what is IRV, inspiratory reserve volume? It's basically a deep breath in. So amount of air your lungs can inhale after a normal exhale. So after you're done with the normal exhale, you can still take more air in, correct? That extra air is called inspiratory reserve volume. Okay? So it's this line again right here, because it's amount of air that you can still inhale after you have finished with a normal inhale. Let's look at ERV, expiratory reserve volume. It's basically a deep exhale. So it's amount of air your lungs can exhale after a normal exhale. So once you finish a normal exhale, I can still tell you still breathe out, right? That extra amount that you're breathing out later on is called expiratory reserve volume, which, as I said, it's this right here. Okay? Now, volumes come together giving you capacities. Okay? So, what is inspiratory capacity? Amount of air your lungs can inhale. So it's this entire thing right here. It's a normal inhale plus this extra inhale. So collectively, the normal inhale, which is TV, and the extra inhale, which is IRV, inspiratory reserve volume, collectively is called IC, inspiratory capacity, amount of air your lungs can inhale. Okay? Let's look at EC, expiratory capacity. Same concept, but in terms of exhale. It's amount of air your lungs can exhale. So it's this amount right here, a normal exhale, TV, plus this expiratory reserve volume, this amount. So after you take a normal exhale, I can tell you to take more exhale out, right? Which is expiratory reserve volume. So expiratory capacity is amount of air you can exhale. You can exhale the normal amount plus that extra amount. Together, it is called the expiratory capacity. Now, before I explain FRC, I forgot to explain what RV means. RV is residual volume, amount of air always left in the lungs. So this amount of air you can never touch. You could never get rid of it. No matter how hard you breathe out, you exhale, you can't touch that amount. It's always left in the lungs. That is called residual volume. So as I said, again, volumes come together giving you capacities. So you have FRC, functional residual capacity. So what is functional residual capacity? Amount of air you can exhale. Amount of air you can exhale. Sorry, I apologize. FRC is amount of air that's always left in the lungs after a normal exhale. Okay? I apologize for that. So the correct terminology or definition of FRC, functional residual capacity, is amount of air that's always left in the lungs after a normal exhale. So after you finish your normal exhale, what is the amount of air you left in your lungs? You have the extra amount, which is expiratory reserve capacity, this amount, plus you have this amount that you can never touch, RV. So collectively, this extra amount plus this amount that you can never touch is called FRC, functional residual capacity. Amount of air left in the lungs after you finish a normal exhale. Now let's look at vital capacity. VC. Vital capacity is amount of air you can manipulate, meaning you can change. So it's all of this. You cannot touch the residual volume, correct? So it's everything apart from basically vital capacity. Okay? So it is expiratory reserve volume, TV plus inspiratory reserve volume. Okay? And then total lung capacity is everything. Okay? It's all of this because it's amount of air your lungs can hold, which is total lung capacity. Okay? Now let's quickly look at the equations for it. No. So, what do you, let me actually go back. What must you know from this slide? You have to be able to identify the different volumes, different capacities, be able to identify them, explain what they mean. Plus, you should be able to do calculations. Okay? In a sense, let's say I give you IRV is 500, and I tell you TV is 100. So this amount is 500, this amount is 100. So what is the amount of IC? Because you add both of these together, which gives you IC, which is going to be 600. Okay? So let's look at some equations. So to calculate IRV, it's IC minus TV. Okay? To calculate IC, it's TV plus IRV. So it's TV plus IRV. Okay? To calculate ERV, it's expiratory capacity minus tidal volume, which will give you ERV. How do you calculate EC? TV plus ERV. How do you calculate FRC? RV plus ERV, because this and this come together giving you FRC. Now, how do you calculate RV? FRC minus ERV. This can also be calculated a different way. So two equations can be used for this one. It's FRC minus RV. So this minus this will give you this. Okay? How do you calculate VC? Again, there are three different equations. So one is ERV plus TB plus IRV. It can also be calculated with IC plus ERV. Or it can be calculated with EC plus IRV. Now, how do you calculate TLC? VC plus RV. What? Oh, there's one more way that you can also calculate this one. So, there are different ways to calculate it, and it's basically based on what the information is given. So if I tell you what TLC is and what RV is, then you can use this formula. But if I haven't given you ERV or IRV, you can't calculate it. So it depends on what the information is given, which equation you would use. Okay? So here's basically a simplified form of doing that. Okay? So these boxes come together. So IRV and TB give you IC. TB and ERV gives you EC. ERV and RV give you FRC. IRV, TB, ERV give you VC. FRC minus ERV give you RV. So FRC minus ERV give you RV. VC plus RV give you TLC. Okay? So these are the ways to calculate it. So IRV, TB give you IC. ERV, TB give you EC. ERV, RV give you FRC. Okay? ERV, TB, IRV give you VC. FRC minus ERV give you RV. VC plus RV give you TLC. Okay? Okay. Question 3. Okay, so let's work to this together. It's asking you what is IC. So what is the equation to figure out IC? TB plus IRV gives you IC. Okay, so you have to plug in the values. TB tells you it's 300. Okay? IRV tells you it's 200. Which 300 plus 200 gives you 500. Okay? So the answer is this right here. Okay, so this equation tells you what is VC. So first of all, you have to figure out the equation of a VC. It is IRV plus TB plus ERV, which will give you basically VC, correct? So we have IRV, we know it's 200. We know what TB is, 300. But do we know what ERV is? No, it doesn't give you ERV. But it gives you information where you can calculate ERV. So this time around, you first have to calculate ERV, and then you can plug it in and figure out VC. So what is the equation for ERV? ERV is FRC minus RV. We have these values. FRC is 600. RV is 200, which gives you 400. So then you can plug in 400 right here, because this 400 is ERV. Then you can add these together. So 200 plus 300 is 500, 500 plus 400 is 900. So the answer is 900. Okay. Be able to do this on the exam. Okay. This slide is just showing you how everything always goes from high to low. So in our lungs, this is alveoli. Oxygen is high, whereas in capillary, oxygen is low. So oxygen diffuses out, enters the capillary. In the capillary, we have high carbon dioxide. In the alveoli, low carbon dioxide, so it diffuses out. Same thing right here, capillary versus the tissue. High oxygen, low oxygen, oxygen diffuses in. High carbon dioxide, low carbon dioxide, so carbon dioxide diffuses out of the tissue. So this is what it's showing you. Okay. Now, this is showing you what happens to oxygen once we inhale it and it enters our capillary. It's actually transported by binding to hemoglobin. So here is the alveoli, here is the capillary, and here is basically the red blood cell. Okay? Majority of the oxygen will leave the alveoli, enter a red blood cell, combine with hemoglobin, giving you oxyhemoglobin. So oxygen is transported in our body bound to hemoglobin. About 98-97% of oxygen is transported in our arterial blood bound to hemoglobin. Only 2% or so is actually transported in the arterial blood as being dissolved in plasma. Okay? It just dissolved in plasma. And then about 98% binds to hemoglobin. Okay, so oxyhemoglobin. Okay. One change you need to do, this goes right here. Not this spot. I accidentally put it in the wrong spot. It should be right here. So this slide basically shows you how carbon dioxide is transported in venous blood. So as soon as your tissue releases the carbon dioxide and it enters the venous end, okay, how is it transported? Okay, so there are 3 ways carbon dioxide is transported in venous blood. One of them way is it becomes bicarbonate. Another way that it actually binds to hemoglobin. And third one, it actually dissolves in plasma. So here are your tissues, meaning your liver cells, your kidney cells, your eye cells, your heart cells, etc. They are built up of carbon dioxide. This is a capillary with red blood cells in there. And we're going to see how when carbon dioxide enters a capillary, what happens to them. So 70% of CO2 will diffuse out of our tissues, enter a capillary, and enter a red blood cell. Within a red blood cell, carbon dioxide and water combine via an enzyme called carbonic anhydrase. It's written right here. So an enzyme called carbonic anhydrase will combine CO2 and water to give you carbonic acid. So CO2 and water will combine, giving you carbonic acid. carbonic acid will break down into hydrogen and bicarbonate. Now, this bicarbonate reformed actually leaves the red blood cell. In exchange, chloride comes in. So what is this transport protein called that allows bicarbonate to leave, in exchange chloride to come in? The name of that transport system is alkaline tide or alkaline pump. Okay? So this 70% of CO2 that came in actually became bicarbonate. This is why we say 70% of the CO2 is transported in venous blood as bicarbonate. 20% of CO2 will diffuse out of our tissues, enter a red blood cell within the capillary, bind with hemoglobin. And so 20% of CO2 is bound to hemoglobin. When carbon dioxide is bound to hemoglobin, it's called carboaminohemoglobin. It becomes carboaminohemoglobin. So 20% of CO2 is transported in venous blood as carboaminohemoglobin. And 10% of CO2 will diffuse out and enter a capillary, and it will just dissolve in plasma. So 10% of CO2 just dissolves in plasma and is transported in venous blood as that. Now, depending on what book you use, some books will use slightly different percentages. I tend to use this percent because the older version used this, and these are easier to remember, 70, 20, 10. Okay? This is the percent that you are responsible to know for the exam, for the lecture exam. Now, this capillary that is rich in carbon dioxide will now turn into vein, and now the veins actually go to the lungs where gas exchange occurs, correct? So we have to release that CO2, and it has to enter alveoli. So now we're going to see how the CO2 is released and enters the alveoli. Basically, the cycle is complete opposite. Sorry, so again, this one should be up here. So 70% of bicarbonate that was in the plasma will come back in via the alkaline tide pump. In exchange, chloride comes out. Once the bicarbonate is in, it binds with hydrogen, forming carbonic acid. Carbonic acid breaks up into CO2 and water via an enzyme called carbonic anhydrase. And that 70% of CO2 diffuses out and enters the alveoli. The 20% of CO2 that was actually bound to hemoglobin and it was transported as carboaminohemoglobin, that CO2 will basically detach from hemoglobin and it will diffuse out, enter the alveoli, which we exhale. This amount will exhale too. And then the last was 10%, which will just, which was dissolved in plasma, will just diffuse out, enter the alveoli, which we exhale. Okay. The last thing that I want to talk about in this chapter, respiratory system, is the acid-base disorders. Before we understand the acid-base disorders, a quick review on the pH. So pH scale ranges from 0 to 14. 0 to 7 is acidic. 7 to 8 is neutral. And 8 to 14 is basic or alkaline. Okay? pH and hydrogens are inversely proportional. So as you increase the pH, the hydrogen decreases. As you increase the hydrogen, pH decreases. They're inversely proportional. What is a pH? Concentration of free hydrogens in a solution. Okay. Acid-base disturbance. Acid-base disturbance. There is two main types of disturbance. There's acidosis or alkalosis. Acidosis means your pH is too acidic. You have too much hydrogens in your body. Or you have too much acid in your body. Alkalosis means that you're alkaline. You're basic, meaning you have too much base in your body. Okay? Now, regardless if you have acidosis or alkalosis, there are two main causes. So there is metabolic system and respiratory system. So you could have metabolic acidosis or respiratory acidosis. You could have metabolic alkalosis or respiratory alkalosis. Okay? So there's acidosis, alkalosis, metabolic acidosis or metabolic alkalosis, respiratory acidosis or respiratory alkalosis. Okay? Now let's look at what that each means. Whenever you talk about respiratory system, think of respiratory as CO2. It deals with CO2. Okay? So I'll start with the respiratory, then I'll come back into metabolic. When you say you have respiratory acidosis, automatically acidosis means that you have too much acid in your body. You're acidic. Okay? And respiratory system deals with CO2. CO2 is volatile acid. So think of CO2 as acid. So when you say respiratory acidosis, you have too much acid. You have imbalance between acid and base due to excess CO2. Respiratory acidosis, excess CO2. That's what you have to remember. Okay? Respiratory acidosis means you have too much CO2 causing you to become acidic. Metabolic. Metabolic branch is looking at basically your base, your bicarbonate. So, your metabolic branch is basically imbalance between acid and base, either due to you have too much acid in your body or not enough base in your body. So, in your body, acid and base are equal. Okay? Now you say so let's say this is acid, this is base. You're saying you have metabolic acidosis. You have acidosis, meaning too much acid. That could be either due to you producing too much acid in your body. It could be any acid, HCl, any other acids. Or it could be you don't have enough base. Because you don't have enough base, it looks like your body has too much acid. So there could be two reasons. Either too much acid is being produced, or not enough base. Okay? So, either you have excess acid in your body, and this is not CO2. Anytime it's CO2, then you call it respiratory. So either you have too much acid or not enough base, causing you to become acidic. Anytime it doesn't involve the respiratory system, we call that a metabolic branch. Okay? Now let's talk about alkalosis. Your pH is alkaline, meaning you don't have enough acid in your body. You actually have too much base. Let's start with the respiratory. When you say you have respiratory alkalosis, that means you do not have enough CO2, because CO2 is acid, and now you don't have enough CO2, causing you to become alkaline. Okay? So, key thing, not enough CO2. Now let's look at the metabolic thing. Everything else besides respiratory system, besides CO2, is considered metabolic. So when you say you have when you say you have metabolic alkalosis, okay, that could be either due to you don't have enough acid, causing your base to be high, or you have too much base, causing the disorder. Okay? So metabolic alkalosis could be due to excess base in your body or not enough acid in your body. Okay? Anytime something deals with CO2 levels, you automatically term it respiratory. Anytime it has nothing to do with CO2 levels, but it's still causing you to go under acidosis or alkalosis, we call it the metabolic system. Now, anytime your body detects that there is a disturbance, you have acid-base disorder, your body will compensate. It has to bring the pH back towards normal. Okay? So, the opposite system always compensates. So again, we have two systems, respiratory and metabolic. If your respiratory system is at fault, meaning it's causing you to have that disorder, then your metabolic system compensates. Okay? And in terms of compensation, metabolic system is the kidneys. If you say that your metabolic system is the one that's causing you to have the disorder, causing you to develop the acidosis or alkalosis, your respiratory system is the one that's going to compensate, meaning bring the abnormality back towards normal. Okay? So this is compensation. Do not get this mixed up with the disorder. This is what your body will do trying to bring your pH back towards normal. If you have metabolic acidosis, so if that is your problem, that's your cause, your metabolic system is causing you to develop acidosis, then compensation is done by the respiratory system. As I said, the opposite system. How will your respiratory system compensate? It will hyperventilate. And when it hyperventilates, it releases CO2. Because now you're releasing your CO2, your pH comes back down. Okay? If you develop respiratory acidosis, which is a disorder, so if you're having acidosis due to the respiratory system, then your metabolic system is going to compensate. And as I said, in the terms of metabolic compensation, it's the kidneys. So how will your kidneys compensate? It will increase the reabsorption of bicarbonate. It will actually take the bicarbonate back up, okay? Causing your pH to again go back towards the neutral range. Now, if you have a disorder of alkalosis, so if you have metabolic alkalosis, meaning your metabolic system is causing you to develop alkalosis, then again, your respiratory system is going to compensate. So if you have metabolic alkalosis, your respiratory system is going to compensate. How does your respiratory system compensate? It actually hypoventilates. When you hypoventilate, you retain your CO2 levels, meaning you retain the acid. Therefore, your pH starts to go back down, bringing it to the neutral level. When you say you have a disorder of respiratory alkalosis, meaning you're developing or you're becoming alkaline due to your respiratory system, then your metabolic system compensates. And in terms of metabolic compensation is the kidneys. So what will your kidneys do? It will increase secretion of bicarbonate. So your kidneys will get rid of the bicarbonate in your urine. And because it's getting rid of the base, your pH starts to go back up towards the neutral range. This is acid-base disorders. Okay, so now your job, and you should be able to do this, is I can give you values, and from there you have to determine what type of acid-base disorder has developed. So right here, this is a normal pH, here's a normal CO2 levels, here's normal bicarbonate levels. So based on looking at the values, you have to develop what type of acid-base disorder the person developed. And what would the compensation be, okay? It can work vice versa. I can give you the disorder, and from there, you have to choose which lab values correspond to that patient, okay? So I'm going to actually do the first one, and I'm going to give you some time to do the rest of them yourself, and then we'll go over the answer. So the way you start this out is the first step you always do. Okay, so the first thing you do is always figure out if the values have increased or decreased. That's it, simple enough. So 6.9, here's the normal range, so this has decreased. Here's a value, it's 30. This is the normal range of CO2, so it has decreased. 11, here are the normal values, so you know that it has decreased. Okay. After you have done that, okay, your next job is to basically figure out, are you in acidosis or alkalosis based on your pH. So you look at the pH and just figure out if it's in the range of acidosis or alkalosis. So Example, this one. This is 6.9. pH is decreased, meaning you're in acidosis. Now, because you have figured that out of the 4, you have eliminated 2. Only thing you're left with is respiratory acidosis or metabolic acidosis. Okay? So now next step is you have to figure out if it's respiratory or metabolic. How do you do that? So step 3. You actually look at the respiratory system. So, meaning, I always first, as soon as I figure out if I'm in acidosis or alkalosis, I always like to think of the respiratory system. I think to myself, if somebody has respiratory acidosis, okay, meaning you have too much acid and your respiratory system is at fault. And remember, CO2 is acid. So if somebody has respiratory acidosis, what should the CO2 levels be in that patient? If somebody has respiratory acidosis, CO2 levels should be high because it's acid. So once you get that prediction, you actually compare it with the patient's CO2. So in a person who has respiratory acidosis, they should have high CO2 levels. They have should low. So that tells you it cannot be respiratory acidosis. So what else is left? Metabolic. So if it does not match your prediction, it's the opposite system. So this is metabolic acidosis. Okay. 4th step. After that, you just want to double check. So you look at the bicarbonate levels. And again, you think, if somebody has metabolic acidosis, which is bicarbonate is base, that's what you're looking at. If somebody has metabolic acidosis, what should the bicarbonate levels be? They should be decreased, right? Because it's a base. So that's your prediction. And now you look at the results. Their base has decreased. The bicarbonate level has decreased. So it matches your prediction. If it matches your prediction, that is the system that is at fault. It decreased. So yes, it's metabolic acidosis. You were right. Now, take about 2 minutes to do this. Okay? You can put me on pause, do it. And once you've figured out the rest of them, turn me back on. Okay? All right. So let's look at basically the disorder. This is 7.5, which is increased. This is 55, which is increased. This is 32, which is increased. Next step, I look at the pH. So pH is increased, meaning I'm in alkalosis. Okay. Second step, I always think of the respiratory system. If somebody has respiratory alkalosis, what should the CO2 levels be? If somebody has respiratory alkalosis and CO2 is acid, the CO2 levels should be low. But this person's is not low, it's actually high. So it did not match my prediction, so it's the opposite system. So it's metabolic. I just want to double check my answer. So if somebody has metabolic alkalosis, what should my bicarbonate levels be? They should be high. It's high, so this is metabolic alkalosis. This one, again, you figure out if it's increased or decreased. 7.1, so it's decreased. 48, increased. 29, increased. Now, because the pH is decreased, it tells me I'm in acidosis. Okay. Now, I think, is it respiratory acidosis? If somebody has respiratory acidosis, it tells a person should have high CO2 levels. Is it high? Yes, it's high. So I know I'm in respiratory because it did match my prediction. To double check, if somebody has metabolic acidosis, what should the bicarbonate levels be? Ideally, it should be low. Is it low? No, it's high. So it's the opposite system, which is the respiratory. And the last one. I look at the pH, 7.6 means the pH increase, so I'm in alkalosis. Okay. Again, I think it's respiratory. So if I have respiratory alkalosis, what should my CO2 levels be? Ideally, it should be low. Did it match my prediction? Yes, so then it's respiratory alkalosis. Just double check my answer. If somebody has metabolic alkalosis, what should the bicarbonate levels be? It should be high, but it's actually low. It did not match my prediction, so it's the opposite system, which is respiratory alkalosis. Okay? Last thing, we figured out the disorders. Now let's figure out the compensation. So if somebody has metabolic acidosis, as I said, the opposite system compensates. So if the metabolic system is at fault, the respiratory system compensates. Respiratory system. How does the respiratory system compensate? They have metabolic acidosis. So the respiratory system will hyperventilate, get rid of the CO2 to bring the pH back up. So hyperventilate to decrease the CO2 levels. That will bring the pH back up. This one, metabolic, this should have been written right here. Next one, metabolic alkalosis. So now metabolic system is at fault, so which system compensates? It's again the respiratory system. This time around, you're in alkalosis, so you want to increase your acid levels. So your respiratory system will hypoventilate. So by hypoventilating, you're increasing your CO2 levels. CO2 is an acid, causing your pH to go back down. Now, respiratory acidosis. You know that respiratory system is at fault, so which one compensates? Metabolic. If the metabolic system compensates, how is it going to compensate? In terms of metabolic, it's the kidneys. So how does the kidneys compensate? You're in acidosis, so you want to increase the base levels in your body. Base is bicarbonate, so your kidneys will increase reabsorption of base. By increasing the reabsorption of bicarbonate, the pH goes back up. The last one, respiratory alkalosis. Because your respiratory system is at fault, the metabolic system compensates. Meaning the kidneys. Now, you're in alkalosis, meaning you have too much base in your body. How will the kidneys compensate, or the metabolic system? It will actually increase the secretion of bicarbonate in your urine. So increase bicarbonate secretion. So basically, you're getting rid of your bicarbonate. And once you get rid of your bicarbonate, your pH goes back down, bringing your pH back towards neutral. These were just answers so you can see if you were right. Question 5. Okay, so it tells you the person formation of phosphoric acid. So now that person has too much acid, phosphoric acid. You know that once you have too much acid, you are in acidosis. So you can get rid of this one. You can get rid of this one, okay? So either you can have respiratory acidosis or metabolic acidosis. And it can't be A and D because we always cancel that out, so this is canceled out. Now you're stuck between these two. Now, is this person was prescribed a drug that a byproduct is formation of phosphoric acid. is the respiratory system's fault at all? No. Respiratory system has nothing to do with it. So it cannot be respiratory acidosis. So it has to be metabolic. Everything else besides respiratory is considered metabolic branch. Okay? Question 6. So it tells you she starts hyperventilating. That's the key word. Hyperventilating. When you hyperventilate, you get rid of your CO2. So if you're getting rid of your CO2, that's going to throw you in alkalosis. So you can get rid of respiratory acidosis because you're in alkalosis right now. So now you're stuck between metabolic alkalosis, respiratory alkalosis. It again cannot be A and D, or option E, because you got rid of D already. So you're stuck between A and C. Now you're hyperventilating. It's your respiratory system's fault. Your respiratory system is hyperventilating, causing you to release CO2 and throw you in alkalosis. So it is nothing to do with the metabolic system. The person has developed respiratory alkalosis. And we are done with the respiratory system. It is very important you understand acid-base disorders, how to figure them out, what is the compensation, understand the lung volumes, lung capacities, and be able to do the equations for that. Okay, you will have math in this upcoming test. Second thing, I don't have to give you a chart of the spirometer. You should be able to draw it out yourself, label it, and understand the relationships. And of course, know inhale, exhale, and about surfactant.